I don't think it's ever been this quiet in this building or in this room before. I think I commented briefly Monday afternoon was quite quiet, but our midterms all done in all the courses so far. No more midterms, just projects and assignments and final exams. How many finals do you have this year? 4, 5, 5? 5. It won't be as bad next year. Fourth year usually have fewer exams and more projects for the most part, so I don't know if that's good or bad. I haven't checked on this for a while because I've just been, I don't know, ignoring it or been too busy. I'm not sure what the answer is, but if you haven't filled out the survey yet, then you can pull out your phone and use that QR code to fill out the student opinion survey for this course. I do take these seriously, and I just want to reinforce a little bit, like, in terms of process for professors and assessment and promotion and stuff, whenever you guys get a job, you're going to have like a 6-month probationary period, right? Like that's the law in New Brunswick. You go and you work for 6 months, and basically if you like them and they like you, then you can continue on beyond that point. Professors, when they start, they're on probation for 6 years. And so I'm on a probationary period for another 3 years or something like that. And so for the next 3 years, this stuff will be really important for me. And so if you like my teaching and you think that I should continue to teach here, then I recommend that you share that opinion with the administration. And if you think that I should no longer teach here, then I equally request that you share that opinion with the administration as well. After 3 years, it won't matter for much in that sense on the assessment side, but I like to teach and I think I'm good at it, and if I can get better, then I want you to tell me how I can do that too. Okay, so please go and fill it out and provide some comments to help me improve things going forward. We're almost at the end of our discussion on flexural members. And as far as beams, joists, and girders go, this is the last time we're going to be talking about beams. Okay, so we have one more day to talk about flexural members, which is sort of something a little bit different, but it ties back to the stuff we talked about for columns earlier. Basically, we've talked about everything we need to talk about so far. So we know how to calculate the strength of a braced beam. That's going to apply to our joists. It depends on section class, whether we use ZS or SE in that first equation. We know how to calculate the unbraced moment resistance of sections that don't have lateral bracing to the compression flange. And as far as we're concerned, that's mostly the girders in our example building. And so the girders are unbraced between joists. L is the distance between joists. And we have to calculate the critical elastic moment that might cause lateral torsional buckling in those unbraced segments, and then base our moment resistance off that expression. We talked about shear in our webs. Shear can cause elastic, inelastic, buckling, or yielding of the web, and it depends on the H/W ratio. 95% of the webs in our W sections in the handbook will experience yielding. The rest might experience some inelastic buckling. And then we talked about deflection. And for the most part, for joists, it's easy. Delta is 5WL squared over 5WL squared over 384 EI. And how much load goes into W depends on how much load is going to be permanent versus how much load is going to be applied after the floor is done. So we looked at considering the live only. We looked at considering the live plus a portion of the dead load that might be non-permanent partitions. We calculated delta. And then that had to be less than or equal to some limit, which was calculated based on the length, and then some number that depended on how susceptible the floor was to cracking or delamination or general damage. Okay? So we've talked about everything we need to talk about in terms of the behavior and the strength of these members. And so now we need to start thinking about how we're going to, for a joist or girder with a given shear and bending moment and length that we have to satisfy deflection for, how are we going to select members to be efficient use of structural steel so that we can design those sections and specify them on our floor plans. When we did column design, I showed a curve very similar to this. Short columns experienced plastification, AFY. Then we had inelastic buckling and then elastic buckling. Beams are almost the same. Plastic moment capacity, inelastic lateral torsional buckling, elastic lateral torsional buckling. For our joists, we're always going to treat them as if they have 0 brace length, and so we're going to see that we get some tables in the handbook that tell us for all of the W sections that we might consider using as beams, what's the flexural resistance of that section. And so it'll be based on class 1, 2, or 3, whether or not it's based on MP, MY, or SE times FY. Basically, the handbook is going to tabulate the cross-sectional moment resistance for a fully braced beam, and we can use that to base our joist design on. When we're looking at our girders and they're unbraced, it's going to depend on what the unbraced length is. Sometimes the unbraced length is still going to be short enough that we can get the full plastic section resistance. But if it's sufficiently long, then we need to start worrying about perhaps inelastic lateral torsional buckling. And for really long unbraced lengths, then we're considering the elastic lateral torsional buckling strength. So just like for columns, the handbook is going to give us a series of tables that tells us what the moment resistance is for a bunch of different unbraced segment lengths. Okay, so if you know what the unbraced segment length is, you can look up in the handbook. They calculate what the corresponding moment resistance is in a similar manner to this plot here, and they tell you what the moment resistance is so you can figure out if that beam is going to work for the unbraced segment length you have or not. We also looked at shear, and while this is a similar plot in terms of the shear resistance, we've got plastification of stocky webs, inelastic buckling of intermediate webs, elastic buckling of slender webs. The nice thing, though, for shear is that it doesn't matter how long the beam is. Really, it doesn't matter anything about the beam other than what the cross-section is. Because H over W is always going to be the same for a given cross-section. And so we don't really care how long the beam is. We just need to care what the section is and what H over W is. And like I said, 95% of the time, we're sort of in this range, or 100% of the time, we're in this range. All of our W sections fall within an H over W ratio of 60 or less. And most of the time, that means we'll get 0.66 FY. Sometimes we have some inelastic buckling. The handbook is going to figure that out for you. It's going to say, okay, for this H to W ratio for this cross-section, this is the shear resistance, and it's going to give you that in the table as well. And that's never going to change. You're going to see in the tables in a minute there's a Vmax and a Vmin. We don't care about Vmin in this course. For simple framing like this, Vmax is all we care about, and that's basically going to be equal to the phi AW Fs based on the H over W ratio for that particular section. And finally, we looked at calculating deflection. Okay, and so we looked at superposition in terms of applying it to a series of point loads where we have an equation maybe for a single point load at the middle of a beam. We have an equation for a couple of point loads equally spaced from the supports of the beam, and we could come up with an equation to calculate displacement. This is great if we know what section we have and we know what I is. The problem is we actually need to figure out what I we need in order to satisfy deflection. Okay, so we're basically going to figure out what's the moment demand on our beam, what's the shear demand on our beam, and based on this equation, we're going to figure out what the limit on delta is, and we're going to use that to back calculate a value of I. Okay, so I'll show you how the tables are helpful for us in terms of selecting a section that's the most efficient for the loading that's present on the beams that we're trying to design. Okay, so basically after today, you should be able to identify which shapes make the most effective flexural members, specifically for joists and girders, navigate the beam selection tables in the CISE handbook, again through some of my shoddy camera work today. And the ultimate goal today is to be able to select the least weight section that's going to satisfy the ultimate shear and bending and the serviceability, deflection, limit states for joists and girders. Does anyone have any questions about why those three things are important before we get into doing these things today? Okay. So I've shown you this slide a million times. Well, 4. Exaggeration a little bit. Wide flange sections are great for beams. They're easy to connect because we can fit a little shear connection in the web, connect it to the face of a column or to the web of a girder. And I used this example before. We have a section that is about 200 millimeters deep with 46 kilograms per meter of steel in the beam. Another one that's taller, more than twice as tall, with the same amount of steel in the cross-section of that section. Okay, so they're the same cross-sectional weight, same cross-sectional area, but they're rolled differently, right? So on the left-hand side and the right-hand side, we have two different sections. Did everyone remember which of these two were better for columns? Left-hand side. Great. So the W200 by 46 is wider, right, than the W410 by 46. That means the moment of inertia about the weak axis is going to be bigger. And when we're doing compression resistance calculations, that means that the weak axis buckling resistance is going to be higher than the one on the right-hand side. So these are great for columns. These are better as beams, because the more steel we have away from the neutral axis, the stiffer it's going to be, right? So IX, the strong axis moment of inertia for bending about this kind of direction, is going to be higher. That means deflections would be smaller. And the Z values are going to be bigger, right? We looked at the force developing in the flanges when we have a plastic stress distribution in the beam. We've got plastic stress above and below the neutral axis. The more steel we can get in the flange and the further away we can place the flange, the bigger the moment arm is between the center of the section and the flange. So not only is IX going to increase in this case, but S and Z are both going to increase as well. So they're going to be stronger sections when we look at the bending resistance of these two comparatively. Now, that's 90% of the time. The one on the right-hand side is going to be a slightly better beam, or a much better beam. Does anyone have any sense for whether or not this may be a better beam sometimes? Michael? So why, for long unbraced beams, why do you say that? And so why would lateral torsional buckling be better for the left-hand side than the right-hand side? Exactly. So we'll remember that back here, the lateral torsional buckling strength, MU, the elastic lateral torsional buckling strength, is very dependent on IY, right? So there's no IX in this equation at all. It just has to do with the warping, the twisting, and the weak axis moment of inertia. And so if I was actually to plot those two curves, right, this is the same curve that I showed before, just for two different sections. We've got the cross-sectional strength in the plateau region. We've got the inelastic lateral torsional buckling strength, and then we have the elastic lateral torsional buckling strength for these two beams. And what we can see is, obviously, for well-braced beams, the moment resistance of the W410 by 46 is almost double the moment resistance, right? Because it's really deep, Z's really big, and so the moment resistance, of course, is going to be bigger. However, if we look at the unbraced length, that's going to start to cause inelastic lateral torsional buckling problems. As soon as the bracing between joists exceeds this value, about 1.79 meters, that value is going to be called LU, and we'll see that as well tabulated in the handbook. As soon as the length between brace points exceeds that, we're going to drastically reduce the strength of that beam. And at a certain point, it's actually going to be weaker than the W200 by 46 because the unbraced length is so long. Okay? So a little counterintuitive there, but these shorter beams are wider and therefore more stable against lateral torsional buckling concerns. And they also have much longer lengths that we can have between providing points of lateral restraint to prevent lateral torsional buckling. And at that point, we're still getting the cross-sectional resistance here. LU is 3370. And at that point, the moment resistance of the W410 by 46 is only 30%, 20-30% bigger than for the shorter beam. Okay? So for really well-braced beams, we're going to be using the deeper sections. Joists are fully laterally braced, and so of course we're going to be using deeper sections for those. Most of the time, the joist spacing is somewhere between 1.5 to 3 meters or so. And so even then, when we're looking at girders, we're really playing in this range here from about 0 to 3,000. And so for our girders as well, these sections are going to be better. It would be very rare that you'd see really long unbraced segment lengths. But if you see one, you can start thinking that maybe those sections might be potentially more useful for really long unbraced segment lengths. Are there any questions about that concept before we continue on? Deeper beams are better for short segment lengths. the shallower beams may be slightly more stable for long lengths. Any questions about that before we continue? Okay, so again, we tend to be playing in the short unbraced length section, and so we're going to be focusing on the deeper beams anyway. Oops, skipped a little bit. In the handbook, in the blue pages, the first set of blue watermark pages, you're going to see tables that look something like this. Okay, and so on page 5-22 is what this page is here. And what it's doing is it's going to tabulate for a bunch of different sections here, and the order is kind of weird. It's going to tell you what the shear resistance is, and again, we're going to focus on this left-hand column. This right-hand column we're not talking about in this class because it's not important for us. We only care about shear max, VR max. It also tells us IX. That's pretty helpful because if we back calculate a moment of inertia we need to get a displacement that works for us, then we can figure out what section works. And then it tells us MR for values of the unbraced segment length that are less than the length that we start to develop some inelastic lateral torsional buckling. Okay, so LU here is tabulated for us. That's the unbraced length beyond which we start to get lateral torsional buckling, reducing the moment resistance. And so this section over here shows us the moment resistance considering the unbraced segment and how lateral torsional buckling might reduce that strength. We don't see any entries here in the 2000 column because 2000 is shorter, and so for this we still get the full cross-sectional resistance. But as soon as we exceed LU, for example, for the W530 by 85, its LU is 2110. As soon as we get to 2500, we can see the strength starts to reduce because of inelastic lateral torsional buckling in that range. And then we continue across the page. We can't see the other page, but further to the right, we go on all the way to an unbraced segment length of even 16 meters, which is quite high. Okay? So the column selection tables were all organized by nominal depth and weight, right? So we started with the W150s, got heavier, W200s got heavier, W250s got heavier. In this case, what are we doing here? They're just all over the place, these W section designations. Does anyone notice anything interesting about the way that these tables are organized in terms of why they're provided to us in this order? Does anything stand out in terms of ordering of any of these numbers? Well, if you look at any of these columns, VR is all over the place, I is all over the place, LU is all over the place, but MR, for the length less than LU, we have the moments in descending order, right? We have the maximum moment, and then we come down to smaller moments, and smaller moments. Beams are governed 95% of the time by their flexural strength. And so the first thing that we're going to care about 95% of the time is what's the moment resistance. And so it tells us, or it orders all these sections in terms of moment resistance from greatest to smallest. The other reason it does that, if you look at these tables, and we remember that the second number here is the weight, right? That's the mass in the cross section. We'll see at the top here, we've got a number in bold, the W610 by 82. That is the lightest section here. So we can come down, we've got a 97, a 129, 185, 82, which is similar, but the moment resistance is smaller. 110, 89, 118, 102, 82 again, but the moment resistance is smaller. And we don't get to a smaller second number until we get here, W530 by 74. What this is trying to indicate to us is that this is the section with the least weight that can carry the most moment. Okay, so whenever you're looking at the handbook, at the beam selection tables, the numbers in bold, those are the most efficient section that can carry up to that amount of bending moment. So 90% of the time, we're going to say, okay, if we have a factored moment on our beam of 620, for example, we could pick a W460 by 89 because it's 624, but it's heavier than a 610 by 82. We could pick a W410 by 100 because it's 661, but it's heavier than a W410 by 82. Sorry, 610 by 82. We might, from time to time, if we want to keep girder depths short, that's pretty common, especially in commercial real estate. For a fixed height of building, they want to fit as many floors into it as possible. So the deeper the floor beams get, the taller the building gets for the amount of occupiable space. And so if you have somebody who really wants to keep the building as short as possible and have as many floors as possible, then you might start looking at a W, even a 360 by 110, because that's half the height almost of a 610 by 82. It's heavier by 30%, but it would still work in that case, and you can keep the floors short. So this is listed in descending order of moment resistance. It's grouped by beams that have a most efficient section at the top, shorter sections below, and then the next time we get to the smaller number than 82, we've got 74. That's the most efficient section that can carry up to 562 kilonewton meters. Are there any questions about how these tables work or what you should be looking out for when we're trying to select beams? Of course, I'll show you an example of how to use this in a minute. So we've got VR. We can calculate VF. We just need to pick something with VF as VR is bigger than VF. We can calculate MF, and we just need to figure out which beam has MR bigger than MF. And we still have to figure out whether or not the beam's going to work for deflection. Now, of course, you could just find something that works for moment and shear and then check that it works for deflection. That will work 90% of the time, but as your beam and if your joists and girders get quite long, then you're going to find yourself annoyed that you didn't pick based on IX before. What we're going to do then is we're going to figure out what equation we need to give us delta. So again, this is not a general equation that only applies to this very specific case where we have 3-point loads. But we would calculate delta as PL cubed over 4080I plus PA over 24EI times 3L squared minus 4A squared. And we know that that has to be less than or equal to the length of the beam, which we know, divided by some number, which we should know as well. If the architect tells us we want to put granite floor down over 360, maybe even over 400 if for natural stone like marble. But if we've got carpet or whatever, then it's maybe 300. If it's the roof, it's 240. In any case, we know the length, we know the number we're going to use, we know the distances of our loads, the load, the length, E. The only thing we don't know here is I. So what we can do is we can say, okay, what value of I is required to meet this limit? And all we have to do is rearrange that equation to get a value of I. As long as I is bigger than whatever number we have from the table in the CSA 16 Annex D, divided by the length of the beam, multiplied by all this stuff, that's going to give us the value of I we need to satisfy deflection. Okay, so not only do we calculate VF and MF, we also calculate the I that's required to satisfy the deflection limit states. And then once we have those three, we just go back to the table and say what section is the least weight that has VR that's big enough, MR that's big enough, and IX that's big enough. Okay, that's why these values are provided to us in these selection tables. Does anyone have any questions about this idea of back calculating a moment of inertia that's required for satisfying deflection before we continue? So for joists, this is even easier, right? Because for joists, delta is just 5WL to the fourth over 384EI. And so basically we just get I is equal to, and I'm going to bung up this math a little bit, I'm sure, but okay, so that has to be less than or equal to L over some number. And so I is some number over L times 5WL to the fourth over 384E. Right, so for joists it's even easier because we don't need to do any of the superposition stuff. It's a straight shot to back calculate the required moment of inertia. Okay, so that's what the tables are for. Those are some of the things we need to look out for. How do we use them, and how do we pick some sections that will work for our example building we've been working with all term. This is the example building, right? We've got this 4-story building. We've looked at the bracing. We've looked at the columns. We still have to look at the joists and girders. So today we're going to focus on some of the joists and girders. All of the joists, pretty much, except for the ones on the perimeter, are going to be the same as the one listed here in blue. So if we pick this joist, that works for pretty much all the joists in the floor plan. This girder here is pretty much the same as every girder except for the girders on the east and west walls. And so whatever we pick for this girder is pretty much going to work for all the other girders. Okay, so we're just going to focus on these typical ones. Okay, so we're going to focus on the joist first, and then we'll focus on the girder. And what we want to do is pick the sections for the joist and girder that will be safe and efficient. Okay, so the dead load was 4.8 on this floor. The live load was 2.4. That was from lecture 5. I went through and you know, we don't need to go through the tributary width and shear moment calculations anymore. I trust you can do that step. We did a tributary width calculation yesterday or last day to get the deflection. These are the shear and bending moment diagrams for the floor joist for dead and live loads. We've got 23.6 kilonewtons, 47.3 for live and dead load and shear respectively, 62 and 124 for the moment for live and dead loads respectively. And the tributary area was less than 20, right? Because tributary area was equal to 1.875 meters, which was the tributary width times the length of the joist, which was 10.5. That gives us 19.7. It's less than 20, and so we have no reduction that we can apply to the joist. What's the first thing we need to do if we want to use the beam selection tables to figure out what joist section or what cross section from the handbook is going to work well for the joist? We've got dead and live loads. What do we have to do with these to get shear moments we need to pick beams for? Do we maybe need to factor them? Right, we should factor these. Right, so we care about the shear force, right? So the shear, the maximum shear is at the left and right of the joist here, right? So this is VL, this is VD, VF. There's no other load combination here that's going to cause a larger shear other than 1.25 dead plus 1.5 live, because while there's no snow, there's no wind, there's no earthquake, it doesn't matter what else is there. There is no other load combination here that's going to make the shear bigger than this particular combination. So if we do this, we get 1.25 times, whoops, sorry, not 23.6. I should have oriented these the other way so I wouldn't confuse myself like that. 47.3 kilonewtons plus 1.5 times 23.6 kilonewtons. And we get, for a factored shear, I end up getting anyway, and someone should check this for me to be sure, I get 95 kilonewtons of factored shear acting on that joist. Okay, so dead and live loads, no other loads are present. You can do whatever load combination you want. You can go ahead and do 1.4 W plus 1.25 dead plus 0.4 live. You're never going to get anything that governs compared to the 1.25 dead plus 1.5 live. Right? For joists that are inside, it's always 1.25 dead plus 1.5 live. Okay, you can trust me for that. You don't need to plug through the 20 other load combinations to figure out what the maximum factored shear force is. I really hope I'm done being sick soon. Any questions about that before we continue on? We also need MF. That's 1.25 times the dead load moment plus 1.5 times the live load moment. So 1.25 times 124 kilonewton meters for dead plus 1.5 times 62 kilonewton meters for live load. And when I do that factoring, I end up with 248 kilonewton meters of factored load. Any questions about that factored moment calculation before we continue on? Okay. Now we have delta, right? We come back to this slide and we would calculate delta if we knew Ix as 5WL to the 4th over 384EI. The question is what goes in to W? Or specifically, how do we factor the dead load and live load displacements? In our case, we're going to assume that the partitions, oh boy, I can't talk and write at the same time apparently. So we're going to assume that the partitions are permanent fixtures. What does that mean for our deflection calculations? It means none of the dead load goes into our deflection calculations. If they're permanent, they get installed, fastened before the floor goes down. We only really care that much about the deflection for the amount of deflection that happens after the flooring is installed. And if the partitions are permanent, then we're going to have only live load to consider in our calculations. Okay, so basically we can base our required moment of inertia off of the live load displacement only in this case. And let's also assume that what did I assume? I don't remember what I assumed. What did I do here? Let's assume that the flooring is susceptible to cracking. What does that mean for my deflection calculations? It's the number, right? Whatever number I'm going to be limiting L over the number, that's my maximum displacement. That's going to be telling me that when I do this calculation, this number here is going to be 360. Okay? So, we've got enough information. The IX, that minimum that's required, is equal to number over L times 5 WL to the fourth based off live load over 384E. That's going to be 360 divided by 10,500 millimeters squared. That's the length of our joist, times 5. Our live load, distributed load, is drawn on the floor joist here. So we had 2.4 kPa times the 1.875 meter tributary width. That gives us a live load of 4.5 kilonewtons per meter. Converting that to newtons and millimeters, we remember that a kilonewton per meter is equal to a newton per millimeter. And so we can write 4.5 newtons per millimeter in the equation. We have 10,500 millimeters to the fourth. And I'm not sure why I squared that. It's not millimeters squared over there. Divided by 384 times 200 times 10 to the 3 megapascals. So we could also say, okay, well, the length gets canceled out and really we just get L cubed there. That would be helpful as well. But we'll remember when we're putting this in our calculator, what are we expecting to get as a unit when we have newtons and millimeters? We're going to get what for the moment of inertia? Millimeters to the 4. And we'll remember it's helpful because our table is always going to be presenting moment of inertia in 10 to the 6 millimeters to the fourth. When you calculate this, you want to write it as 10 to the 6 millimeters to the fourth. Otherwise, you're going to have a hell of a time finding a value that works for you in the table, right? If you write it as 4.55 for this section, 4.55 times 10 to the 8 millimeters squared, which is what you're going to get in the calculator, then you're going to be confused when you come look at this table, which is in the hundreds of millimeters to the 6. Hundreds of 10 to the 6 millimeters to the 6th. Okay, so if you were to write this out in your calculator, you would get 1.22 times 10 to the 8 millimeters to the fourth, right? That's what you'd get in the calculator. You want to move the decimal to the right 2 times and write it as 122 times 10 to the 6 millimeters to the fourth. Does anybody have a calculator that does like engineering notation? Or does everybody get something like scientific notation is something point something to the power of whatever? Does anyone get like 10 to the 6 when they do that calculation? So like engineering notation is like scientific notation, except we only do 10 to the powers of 3, 6, 12, etc. And so if you have engineering notation on your calculator, it might give you 122 times 10 to the 6. Otherwise, this is, that's scientific notation. And this is engineering notation. It's just because it works well when we're doing unit conversions using metric units, we don't get confused when we're doing our metric unit conversions. Okay, so what did we do here? We have the factored shear on the beam. We have the factored moment on the beam. And we have the minimum moment of inertia that would allow us to satisfy deflection limit states. So what do we do with these numbers? We just need to look in the section of the handbook with the selection tables, and we need to find a beam that has a moment resistance that is at least equal to MF, a shear resistance that's at least equal to VF, and a moment of inertia that's at least equal to the minimum required to satisfy deflection. Okay? So I'll do my best here. Again, on calculator, what would I say? On the camera, let me rewrite these on the boards just to remind you. VF is 95 kilonewtons, and sorry for people watching the video later. I'm just writing stuff on the board. MF was, see, this is why I have to remind myself of these things, 248 kilonewton meter. IX min was 122 times 10 to the 6 millimeters to the. Right, so I'm looking for 122, 248, and 95 in those tables. So if you start in the handbook and kind of go all the way to the start of the tables, the table on page 5-24, and we're going to start looking first for a moment that's going to work. And we're going to see none of these moments actually work, right? So the biggest moment on this table is 242. And so that's not quite going to work for us, right? So maybe a W360 by 45 was close. We're going to turn the page at the bottom. And as soon as we look at the bottom, page 5-22, we're going to see that a W410 by 6 has a moment resistance that works. Right? And remember, any of these would work here. W200 by 71 are actually in moment resistance, but it's heavier. 71 compared to 46, that's like 60% more section. A 310 by 52 could also work, but it's heavier. So a W410 by 46 is the most efficient that will provide the moment resistance that's required. And if we look at VR max, right, VR max is the 578. Is that enough? That's way more than we need, right? We need 95 kilonewtons of shear. It's the moment that's going to be governing the strength of these joists, and so we don't really care about the shear. It's plenty. And then the last thing we're going to look at is IX. IX for this section is 150. We needed 122. Is this section acceptable? Yeah. So we're picking it based on moment, and in terms of not working, but it works for us here. We've got enough I, we've got enough V, and so we're going to pick a W410 by 46 to be the joist in our example building. Okay. Why did I not look at any of these values of moment when looking at my joist? I went straight to the fully laterally braced bending moment resistance. Why do I not care about any of these, right? My joist is 10 meters long. Should I not be looking way out here at like 32 kilonewton meters of strength? Why am I looking at this column here, fully laterally braced? Yeah, because it's a joist, and joists are fully laterally braced. That's how we build buildings. It's connected to the steel deck. It's a fully laterally braced beam, and so we base the strength on the fully laterally braced moment resistance. Okay, so we're going to, pick W410 by 46, and that's going to work for most of the joists floor. Any questions about that example joist selection before I move to the girder? Okay. So let's look at the girder then. We looked at this for shear, right? We looked at the shear resistance of a W, I forget what it was, not important, but we looked at the factor. The tributary area for this girder is 59.1, and so whatever we calculated for live load load, we can reduce those live load effects by 30%. So we multiply them by 0.707. And so this is, oops, why am I writing like that? This is VF star, the reduced factored shear, or the reduced, Jesus, that's not right at all. That is reduced live load shear. There we go. And that's the reduced live load moment. Okay. So again, when we're looking at the factored forces, there's nothing other than dead and live load acting on this particular component. And so we're going to look at the factored shear force. That's going to be 1.25 times our dead load shear plus 1.5 times the reduced shear force. That's 1.25 times 142 plus 1.5 times 50.1. And we end up with, in this case, a force of, where are the rest of my, I get 113 kilonewtons, and I recommend that somebody double check me on that one. 213 kilonewtons of factored shear force. We also need MF, 1.25 times something different, Katie? Yeah. What did you get? 253. Why do I have that as a shear force? Sorry. You're right, I had the wrong calculation there. Thank you for catching that. So when I did the calculation, for some reason, the old joist live load in there should be 253. Cool? Katie, it's the same number? So the factored moment, we have M live star. I should be sure that I'm using moment there. I am. So you get 1.25 times the dead load moment, which was 354, plus 1.5 times the live load reduced moment, 125. I get MF is equal to 619 kilonewton meters. Okay. Questions about those factored load calculations before we continue on? Okay. The hardest part here is the deflections. Okay. Again, we're just going to focus on the live load deflections. Right. So there's no dead load here that we're considering, and we're at permanent partitions, and so we're not going to include. We're basically saying, well, the delta dead that occurs after the floors. And sorry, you have a question? Oh no, what did I do? I have 125 kilonewton meters. I have 300 and, oh, I wrote 345, like a moron. Okay. Oh boy. If I do 54 instead of 45, I never thought I was dyslexic, but sometimes I wonder if I might be a little bit. 630 kilonewton meters, is that the same number? Great, thank you. So these are the correct values, 253 of shear and 630 of bending moment. So it's actually convenient because we happen to have 3 equally spaced point loads on our beam. We came up with an expression that works for this one unique case of 3 equally spaced point loads on our beam. Here we're looking at this equation, right? I has to be greater than or equal to some number over L multiplied by the stuff in the brackets. We just have to remember what A and L are in this case, right? So here for us, A is going to be this value. That's 1.875 meters, which is 1875 millimeters. The length of our girder overall is 7.5 meters, or 7,500 millimeters. Okay, so those are the values that go into this equation for deflection. So the minimum moment of inertia that we need our beam to have is going to be 360, maybe I'll write out the equation again, over L, multiplied by, and we'll remember here as well though, this is P that we're using from the loads applied to the girder, but because we have a live load reduction factor that we can apply when we're calculating deflection, we're going to include that as well on our calculation. Okay, so we're going to include the live load reduction factor on the live load point load that we're including in our deflection calculation, times A over 24E times 3 times the length squared minus 4A squared plus live load reduction factor times PL times L cubed over 48E. And if I do that, I'm going to plug in the values, 360 over times 0.707 times 47.3 is the live load point load on the girder, times A, which is 1875, 24 times 200, 10 to the 3, multiplied by 3 times 7,500 squared, minus 4 times 1875 squared, plus 0.707 times 47 kilonewtons times 7,500 cubed over 48 times 200 times 10 to the 3. So the most involved calculation in terms of writing out all the stuff in the calculator, but when I do that I get 191, again arranged such that I get 10 to the 6 millimeters to the 4th. And I'm pretty confident in that when I caught a mistake just before I wrote that out, so that should be the right value. You don't need to go through and check that in your calculator. We'll be here until 9:30 if that's the case. So we have a factored shear force of 253. We need our beam to have a factored shear resistance bigger than that. We have a factored moment of 630 kilonewton meters. We need our beam to have a factored moment bigger than that. And we calculate the minimum moment of inertia required. It's 191 times 10 to the 6 millimeters to the 4th. And we need a girder section to have a moment of inertia higher than that. Okay, this is actually helpful because instead of trying to do my shoddy camera work, I actually have that will work for our purposes. Okay, I'll get rid of those red lines here. And maybe I will ask all of you, which of these sections is the section we should pick based on what's shown on these selection tables here? So we had VF is 253, MF is 630, IX min is 191, 10 to the 6. Okay? Which of these sections is going to be the most efficient section for our girder? So the first thing we need to consider, well, our girder is laterally unbraced, right? Or I guess we could say it's braced at intermediate points. The girder is braced at the joist, and so L, when we're calculating MU, the unbraced segment length is equal to 1875 millimeters, right? So the first thing we should do is we're going to look at MR, because that's what we always do, at the right MR. Okay, so in our case here, we don't have an unbraced length that exceeds LU 2500, then I would look at this table, right, or this column and see which one has the moment resistance that works. In our case here, LU 10, 2650, 5000, blah, 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 blah. There's not a single LU value in this column that's smaller than the unbraced segment length we have. So if we look at this table, our unbraced segment length is shorter than LU for all of these sections. And so I don't really care, right? Maybe I'd go from 484 to 483 if it was in here somewhere. But torsional buckling is not going to reduce the moment resistance for our girder in this case. We can be safe looking at this first column here, and we don't need to consider any other unbraced segment lengths. We're going to get phi MP or phi S. And so if I look here, right, efficient section, W460 by 60, that's not strong enough. 530 by 66, that's not strong enough. 530 by 74, strong enough. But a W610 by 82 has a factor resistance of 683. That's bigger than 630 in bending. All of these other sections, well, some of them might work. Everything down to a by 110 would work, right, based on the bending moment resistance. If I really wanted a short girder, by 110, but it's 30% heavier than a 610 by 82, so I'm going to use less steel and provide more margin of safety, I guess, with 683. Shear, not an issue. It's 5 times stronger than it needs to be. Deflection, not really an issue. It's almost 3 times stiffer than it needs to be in order to limit the deflections to a reasonable value. So in my case here, I'm going to pick this W. Why is my pencil not working all of a sudden? So I'm going to pick this W610 by 82, and that's going to have a moment resistance that's bigger, a shear resistance that's bigger, and a moment of inertia that's bigger than required for me to satisfy all the things I need to. Oh, because I'm an eraser. That would help if I was not an eraser, wouldn't it? So I'm going to pick a W610 by 82 because MR is bigger than MF, VR is bigger than MF, and IX is bigger than, IX minimum to satisfy deflection limit states. Okay, so we went through shear, moment, and IX calculations for our joist and our girder. We used the selection tables to pick sections that had MR, VR, and IX that were bigger than the values we calculated. And again, we picked the bold values because in this particular case, we were interested in finding the most efficient section that would work, though I'm not ignoring the fact that there were other sections there that might work, and you might pick those for other reasons. Does anyone have any questions about anything we did for the joist or girder, how we pick beams before we move to close lecture in the morning? Okay. Well, now you should be able to identify which shapes make effective flexural members. They're usually the deepest sections. Joists and girders should be able to navigate blue tables, the beam selection tables, figure out what they mean and where to find values, and ultimately use those tables to select the least weight section by ultimate and serviceability limit states, ultimate being shear moment, serviceability being deflection. Any questions about anything we talked about today before we wrap things up? All right, see everyone Friday.